Now we have evaluated and solved some log equations before. One of the simple ones that we may have done in the past was something like log 3 of 27. Now, working with logs, you're still not quite used to them, but at this point I'd say, well, if we don't know what this is, we can make it equal to x, and then we could change it to exponential form, because the base is 3, the exponent is x, equals 27. And that's basically what log 3 of 27 means. 3 to what power is 27? And once it's like this, you would say, well, I can write 27 as 3 cubed, so x has to be 3. And we use that strategy of writing things as the same base in order to solve for them. The only way we can change from log form to exponential form is if we have a single log. So all of that practice that we were doing before sort of gets put into place here, because right now I can't evaluate these because I don't know what 9 to what power is 72, 9 to what power is 6. Those are not things that I know because they're not powers of 9. But maybe if we can combine these, they might become a power of 9, and then I'll be able to solve them. So our first goal here is to see, can we write these as a single log, and then can we change them to exponential form, because that might help us understand what it's equal to. So here, the 3 out in front, because we can't combine subtracting until it's a log minus a log, because that's what our log law says. And now 6 cubed is equal to 216 divided by 72. So this simplifies to 3. Kind of nice. Now it's a single log. Now we can say, well, if I made it equal to x, and I thought of my exponents, well, this is the base is 9. I don't know the exponent. 9 to what power is equal to 3? That's what that log means. And now we go to our powers chart and say, have we learned a way to write these both as the same base? Well, 9 is 3 squared, so I could change 9 to 3 squared. And some of these you'll be able to see. Can you see what x is right now? No? Then this is a good strategy. If you could see what x was right away, then you could just write it out if you wanted to. Just like this last one, when I had 3 to the x equals 27, you might have been able to see that x was 3 right away. You wouldn't have to write 3x equals 3 cubed, but this is a nice strategy, getting things as the same base, especially when you can't see it right away. So for this one, now that I've changed to 3 squared, that means I have 3 to the 2x equals 3, and 3 is the same as 3 to the 1. And now that we have the same bases, you know that 2x has to equal 1. So, and this is where we're actually taking log base 3 of both sides, but we don't write that down, and just have 2x equals 1, so x is equal to 1/2. So again, just to recap, what did we all do there? Well, first, we wanted to use this strategy that if I can change it to exponential form, then I can solve for it. Right now, if I made it equal to x right at the beginning, I can't change it to exponential form until I get to these places where I have a single log. You can't change it to exponential form in the first step because you have 2 logs. And there's no, our definition of a log is only when we have a single log. So for part B, we have a similar situation. We have a whole bunch of logs that we don't know what it's equal to. We're going to see if we can combine all those to a single log. When you're combining things to a single log, you always use the power rule first, so all the numbers in front get put in as exponents. And then we can use our shortcut that we've learned about combining, adding, and subtracting. Whatever is added will be multiplied, and whatever is subtracted will be divided. So if I look through this, can you see that only the log 4 of 3 cubed is subtracted? So that's going to be why the 3 cubed is the only thing on the bottom. And the 6 squared and the 12 are multiplied on top. Now, if this were a non-calculator question, I would highly recommend not multiplying 6 squared to get 36 and then trying to multiply that by 12. Your numbers are going to get really big. What we're going to do is, you agree that 6 squared is 6 times 6? Can you see that 6 is 3 times 2? So that would be 3 times 2 times 3 times 2. I'm going to give myself a little bit more space here. And 12 is 3 times 4. Can you see why I'm doing that? Because I have 3 3's on the bottom. And if I break up the 6 to 3 times 2 and the other 6 to 3 times 2 and the 12 to 3 times 4, then these 3 3's will cancel with those 3's on the bottom. And then I'm just left with 2 times 2 times 4, which is 16. Now, if we made this whole thing equal to x all the way along, because we don't know what it's equal to, we now have a single log. And how do you solve a single log? Well, it's asking 4 to what power, and that's what I don't know, is equal to 16. So we need to solve for x. Is this one that you could see? What's x? 2. And if you wanted to, you could change 16 to 4 squared and have the bases the same and get x equals 2 that way too. So again, the idea is, for these evaluate ones, can we get it to a single log? Because once we get it to a single log, we can change it to something that we're not as comfortable with, to something that we're more comfortable with, and then we can solve it. And question number 13 is one you can do for practice here.